Hi there again. This video is going to briefly introduce some of the properties of metals and nonmetals, most of which you're probably familiar with, and then talk about the trends of the periodic table, which I'm going to call PToE, probably for the rest of the lecture here. So just to start out, these are the comparisons between how the periodic table used to be organized to now, to which it's organized according to our modern theory, the modern atomic theory. So Mendeleev was one of the first scientists to start to see that there were some trends in properties of elements. So he used properties or similarities in properties to group elements and then ordered them in order of increasing atomic mass. There were a few exceptions though. Tellurium and iodine have slightly opposite masses than what he thought. However, the properties that he saw kind of trumped the differences in masses, so he organized them separately. He didn't know about the whole atomic structure like we do now. So in our modern times, we order an increasing atomic number, which is the same thing as our proton number. That's because we know a little bit more about the signature proton number in individual elements and how that's kind of like the atomic fingerprint. That is definitely going to be an indicator of the identity of the element. And then we had to expand the periodic table at the higher period numbers because there are more orbitals for these elements to take on. So that's why we have this big chunk in our periodic table. It looks like this. We've got our little D block, and then there's this expansion of this group right here, and that's where we have our F block. So it would look funny to insert this F block into the periodic table, so we kind of put it outside and said insert here. A couple of metals, properties of metals and nonmetals. Remember, we have chemical properties and physical properties. Chemical properties relate to the reactivity of these individual elements. So the reactivities are controlled by electrons. So that is one thing you definitely need to know. And I'll explain why metals usually have 1 to 3 electrons in their outer shell and why nonmetals have between 4 and 8. I'll show you that on the periodic table in just a second. But the outer shell, whenever I say outer shell electrons, those are also known as valence electrons. That's a word that you need to be familiar with. Valence, which you can think of it like this. It means very outside level of electrons. We'll get into these electronegativities in just a second. Metal and nonmetal physical properties you're probably very familiar with. Metals are malleable, ductile. You can see the definitions there. They're great electrical conductors and heat conductors. And then they have their metallic nature to them. Metallic meaning metal. They have a sheen, a luster to them. Also, they are solid at room temperature except for mercury, which is liquid at room temperature. Nonmetals are completely opposite. They're brittle, they're non-ductile, they're poor conductors of heat and electricity. They're thin whenever they're into a sheet, and they're solids, liquids, or gases at room temperature. Most of them are gases. There are a couple liquids, like bromine is a liquid, and very few solids like iodine. And these are I2 and Br2 because they're diatomic. We're going to get into that as well. Diatomic. My penmanship with this is fantastic, sorry. Okay, you already know groups and periods, the names of them and where you find them on the periodic table. Just want to give you a quick reminder. Groups are the ones that go down. They're the columns, and we are really only referring to group 1A, 2A, and all over to 8A. We don't label these a specific number group. On the periodic table, you'll notice there's 2 designations. We skip the transition metals when we're counting, so it goes 3, 4, 5, 6, 7, because these are going to relate to the valence electrons here as well. So VE, valence electrons. So groups have similar properties, like the alkali metals are reactive. The halogens over here on group 7 are very electronegative, and so on. They have similar properties because they have similar electron configurations. The electron configuration specifically that I'm talking about is that they have the same number of very outside electrons, those valence electrons. Okay, so what Mendeleev and a couple of other people saw was that as you travel through group 1, group 2, and on through 8, the property that we were interested in repeated every 8 elements, every 8 elements, every 8 elements, every 8 elements. So there was some periodicity. periodicity to the nature of the elements, which is why we get the periodic table of elements. Every now and then you would see the same property come up over and over and over again. That's what we refer to as periodic law, repeating in properties. The representative elements are those two big columns. So when I draw my periodic table, this is beautiful, I know. It's the elements that are on group 1 and 2 here, and then 3 through 8 over here. So these are called the representative elements, and they are labeled our A groups. That's what I was saying about the designation on your periodic table. They have electrons in S and P sublevels, and then you know these names already. 1A, 2A, 7A, and 8A are the individual names written here. The transition metals are called the B groups. They are not the representative elements. One important thing that you need to know about the transition metals is that they produce colors. Copper, for example, copper 2, whenever it's in solution, is blue. Cobalt can be either pink or blue. There's a couple of others on there, but those are two that are kind of important. And it's because of the absorption of light in the orbitals in D block. Okay, a little bit more on valence electrons, just so you're clear about exactly what we're talking about. The valence electrons are the outermost orbital shell or sublevel. And so the reason we talk about valence electrons so much is because they have the highest energy electrons, which makes them very, very reactive. So when we are doing our chemical bonding in our next unit, you'll know that when I say it's able to lose 1 electron or gain 1 electron, it's because its valence shell is allowing for the loss of 1 electron or the gaining of 1 electron. So it's all about if there's room in the valence shell or if it has the desire to lose the last electron in its valence shell. And then this is what I was just telling you about earlier. Elements with the same number of valence electrons have similar chemical properties. And this last point down here about the group number, this is a trick. Anything in group 1A has 1 valence electron. Anything in 7A has 7 valence electrons, and so on. So the group number, the A group number, is specific to the number of valence electrons that that element has. Okay, so now that we know a little bit about the reactivity and the periodicity, let's talk about the trends. There are 4 trends that we see in the periodic table. So these trends are just kind of like describing to you how you can predict the size of an element based on where it is on the periodic table, or you can predict the ionization energy and so on. So I'm going to abbreviate these as AR, atomic radius, IE, ionization energy, EN, electronegativity, and EA, electron affinity. I'm going to go into detail about each of these 4, so you can write this down right now, or in just a minute. The 2 things that we're mainly concerned about that helps us decide on the trends, these are the 2 factors that we are concerned about, are effective nuclear charge, which we label as ZEFF. The reason this is the Z is because the Z number is the same as the atomic number. This is why ZEFF, nuclear effective charge. The nuclear effective charge is mainly a period trend, or a period trend factor. Factor. And what we do is we look at the number of protons in a specific element, in the nucleus of the element, to decide how strongly it attracts its own electrons. So if you're comparing lithium, which has 3 protons, and then go all the way across the period to fluorine, which has 9 protons, they're in the same energy level. So they're in the same period, which in this case is period number 2. So lithium having 3 protons versus fluorine having 9 protons. 9 protons pulls on its valence shell electrons much, much, much stronger than lithium does. So the effective nuclear charge of fluorine is much greater than lithium. Smaller effective nuclear charge. All right, so that's something you're talking about the protons, which is a period kind of a factor. The shielding effect is a group factor. So why I say it this way is because sometimes I'll have you compare an element like lithium and fluorine that are on the same period, and what you're mainly concerned about explaining is its effective nuclear charge. If I ask you to compare lithium to something in its own group, like maybe francium, which is way down here on the bottom, you're going to be describing the shielding effect. So here's the shielding effect. Whenever you have lithium, and I'm going to draw it like the Bohr model, lithium, there's its first energy level, and there's its second energy level. Oops, I'm going to draw these little electrons in here too. Lithium has 2 energy levels or 2 rings, and that's it. Francium, on the other hand, it's in the 7th group, so it's got 1, 2, 3, 4, 5, 6, 7 orbitals. So just basically looking at this, you can see that francium is much larger because it's got all these orbitals. And it's also got all these electrons, and you can barely see these electrons, but they're all on the inside of the rings. This lonely electron way out here in the 7th energy level, this electron is shielded. My penmanship's great again. Or blocked from the nucleus. So when I say it's blocked from the nucleus, it means it can't be attracted to the nucleus. It feels no attraction to its own nucleus. That means that this electron is going to be very, very reactive. Rx means reactive, meaning that it's not going to feel any attraction for its nucleus. It's going to react with something outside of the atom much, much easier than lithium, whose lonely electron way out here feels very attracted to its own nucleus. It's very close to it, so there's less shielding in lithium than there is francium. So we'll get into details about these as we compare the trends, but these are the 2 factors you'll be mainly describing, and electron distance from the nucleus is directly related to the shielding effect. Okay, let's look here. The atomic radius, which is mainly just describing the radius of an atom or the size of an atom. As you go across a period, here's my little bitty periodic table over here. As you go from lithium to fluorine, like I just did, the ZEFF, or the nuclear effective charge, gets larger. As the pull or the charge gets larger, it attracts its own electrons better. So if you attract your electrons better, you are pulling them in. If you're pulling them in, you're shrinking the atom. So this is probably the most important point that you need to know for across a period trend. The distance from the nucleus doesn't change because we're in the same energy level. Therefore, the shielding effect plays no role because we're on the same energy level. The shielding effect is only going to take place if we're talking about a group, going down a group. So in the end, moving from left to right, the atomic radius is going to get smaller. And that's because the ZEFF, the nuclear effective charge, increases across a group. So if you were trying to describe who's larger, lithium, who has less effective nuclear charge, is larger, and fluorine is smaller. Whenever you're looking at the atomic radius and you're going down a group, it's really similar. But we're not considering the effective nuclear charge anymore because it's not changing. It's not the important part. It's the distance from the nucleus, because as I go from lithium to francium, like I did just a minute ago, we have 2 orbitals or 2 energy levels to consider, and then this one down here has 7 energy levels to consider. So the shielding effect is definitely the key here. The energy level, the valence energy level, is very far away. And that is just naturally going to be increasing the radius of the atom. So the way I remember this is that when I have my periodic table in front of me, I put an arrow going that way and an arrow going that way. The atomic radius increases to the left on a period and increases down a group, and I put atomic radius like that. I'll show you how to do this with my fingers whenever I see you again. Ionic radius is a little bit different. So an ion is after you've had an electron being removed or added. The cations are our positive ions. So how did it get positive? It had to lose an electron. So if I was talking about lithium again, lithium, which has 2 electrons in its first orbital, and then 1 electron out here, when lithium becomes lithium 1+, lithium is no longer able to have that outer energy level. This one goes away. It gets lost. So we've shrunk because we've lost the outer ring. We lost the valence shell. So the atomic radius of cations are always smaller because lose valence shell or valence orbital. Anions are opposite. They've gained an electron. So this is not really about gaining a shell. It's about repulsion. Okay? So electrons and electrons and electrons all floating around together in the same energy level repel each other. So if you repel each other, you spread out from one another as well. That's naturally going to make the atom out on the outside larger. There's also the factor that the protons within can't efficiently attract all the electrons, therefore the electrons continue to repel more. So that's going to, in the end, result in a larger atomic radius. All right, next one, ionization energy. This is pretty much self-explanatory. Energy needed to make an ion. However, the ion that we're talking about is to make a cation. So you want to take an electron. And when you take an electron, you leave a positive charge at the end on the atom you took it from. So let's think about the ability to remove an electron. If an electron, let's just talk first before you start doing the notes. If the electron is closer to the nucleus, then it's difficult to take because of the attraction it feels between a positive charge and a negative charge. If the electron is far, then it's easy to take because it has no attraction for its own nucleus. So if you have a larger atom, think about it. Larger atom, valence shell is really far away. That means it's easy to take an electron. If you have a smaller atom, it's hard or difficult to take an electron. So when I say easy to take electrons, it's probably going to be a small amount of energy needed. So a small amount of energy needed. Okay, so let's now fill in the blanks. It takes less energy to remove an electron far from the nucleus and more energy to remove an electron in a lower, in a lower period. So as you kind of are trying to graph out how you want to remember this on the periodic table, I say increases and decreases like this, but I actually prefer to draw my arrows in only the increasing direction. So for the periodic table, it increases from left to right, and it increases from bottom to top. Previously, so this is ionization energy. So previously we had this one, opposite directions, increasing to the left and increasing down, and that was for atomic radius. This is how I remember the different trends. Atomic radius is the only one that goes in the opposite direction. Ionization energy and the rest of them will actually increase up and to the right, as is indicated here. Electron affinity, if you know what the word affinity means, then this should make sense. Affinity means that you love that, whatever it is, you love it, you want it. You have a high attraction for that. I have a high attraction for chocolate. Just happens to be my weakness. So, if some atom has a high affinity for an electron, it has a high electron affinity. And it's the energy actually needed to make an anion, so it's attracting that electron, and it's going to make the anion, which has a negative charge. So this one also increases to the right, as we just had with the ionization energy. Why? Whenever you increase the energy needed to make that anion, sometimes we're going to talk about how the energy is exothermic and it's releasing that energy. Sometimes we're going to talk about how it's endothermic and it's taking in that energy. It doesn't exactly matter which one I'm talking about right now. I just need you to know the trend, and we'll get into a little bit of the detail about why it increases as you go over here towards the halogens and why it increases as you go up, or decreases when you go down. But it's similar to the ionization energy trend. So increasing active electron affinity from larger atoms to smaller atoms, it increases. And then you can also see that indication from the bottom of the periodic table to the top. Last one, electronegativity. And this one you'll see a lot when we talk about bonding, so pay attention to this one. This is one of the most important ones. Electronegativity means that you've got the ability to share an electron in a covalent bond, and you probably know that covalent means that you share electrons, but sometimes there's one partner in the shared nature that doesn't share as much, that actually hoards the electrons more. So when you're talking about water, we all know water looks like this. There's water, and we know that water is polar. That's probably something you've heard before, but why is it polar? It's because in this shared bond right here, there's an electron and there's an electron, and there's an electron and there's an electron. Each bond has 2 electrons. Oxygen happens to be more electronegative, so these electrons hang out towards oxygen up here more often than they do down here by hydrogen, as do these electrons. These electrons in the shared bond hang out up here with oxygen, so oxygen's got a very negative area around it, whereas hydrogen has a slightly positive area around it. And that's just because in the bond, oxygen is pulling the electrons up towards it. Hydrogen doesn't have the ability to pull up the electrons towards it. That's all because of the electronegativity. Electronegativity increases the same way ionization energy, electron affinity does, so you can remember them all the same way. It increases up and increases to the right. This one's pretty easy to see the difference of why it increases to the right and up, because over here, let's go from this atom, which is kind of small, versus one down here. I'm going to draw it way down here, but one that's really, really large. The atom that's really small has a nucleus that's fairly close to the surface. This atom that's down here is really large. It's got a lot of rings around it. This nucleus is not close to the surface. So this has less electron shielding. Less electron shielding means that the protons in the nucleus attracts the electrons in a bond more. So that's how the group works. Same situation whenever you're going across a period. The effective nuclear charge increases as you go this way. So there's a stronger proton pull or attraction on electrons, especially in bonding pairs of electrons, on the right side of the periodic table, because there's a higher effective nuclear charge over here. The lesser effective nuclear charge means that the protons can't attract as well. And so they don't have the need or the electronegativity, the desire to take electrons in a shared bond. So here's a summary of all those, but like I said, this is the best way I think to remember it. Atomic radius increases to the left and down. Everything else increases to the right and up. So you'll see me write this on the board a lot like this. Okay, so when you're comparing, usually I'll have you compare across a period or down a group. Sometimes you'll have to kind of make a little puzzle and figure out who's the biggest or has the highest electronegativity or whatever. So for each of the following pairs, tell which has the largest ionic radius. So let's look at the atomic radius first. Aluminum is here, boron is here. So this is going down a group. If you remember to draw this right around your periodic table, you'll have no problem at all. Atomic radius increases down a group, so aluminum would have the largest ionic radius. Ionic or atomic radius, either one. because both of these have 3 valence electrons, so they will lose 3 valence electrons to become Al3+ and boron 3+. Either way, when they lose their 3 electrons, they're going back 1, 2, 3, or aluminum 1, 2, 3. Still, between these two, the electron configurations that they kind of act like, they're still, aluminum's still going to be the larger. All right, between oxygen and sulfur, oxygen's here, sulfur's here, same situation. The one that's lower down has the greater radius, and this is only because of the orbitals being added to radius. The electrons are farther from the nucleus. Between chlorine and bromine, same situation. We've got the lower one being the larger one. Sodium and aluminum is a little different. We've got sodium and aluminum, which are in the same period. So when you're comparing across a period, you don't think about how far the electrons are from the nucleus. What do you think about? You think about the effective nuclear charge, ZEFF, effective nuclear charge. So if you look at these two, sodium only has 11 protons, whereas aluminum has 13 protons. Who pulls more? Aluminum pulls more. If it pulls more, it gets smaller. Sodium can't pull as much, so it doesn't attract its outside electrons very well. So it's definitely going to be the larger. And you can see the atomic radius trend increases to the left. That definitely makes sense. So I'm explaining it to you and telling you the trick. Sometimes you need to identify. If you're identifying it, just simply choose. No explanation needed. On the exam for the MSL and my exam, you will have to explain it in terms of the 2 factors that we're mainly considering, which is the effective nuclear charge and the electron shielding, or the distance from the nucleus. So when you have to explain, you have to explain it in these 2 terms. Which of these has the lowest ionization energy? So let's draw our little trick here. Ionization energy increases to the right and up. Lowest would be down here closest to this corner. Highest would be up here closest to fluorine. All right, so between calcium and zinc, comparing these, who is closest to the corner? That would be calcium. So why does this have the lowest ionization energy? Because the calcium atom is larger than the zinc atom, which is smaller. Larger atoms, their electrons are farther away from their nucleus. Therefore, you can take that electron with greater ease. Let's skip to nickel and iodine. So iodine's over here, nickel's up here. This one's a little tricky because this nickel is not in the same period or the same group of iodine. So then you have to kind of think about 2 things. You know that the atomic radius gets larger as you go down a group. So iodine seems like it's pretty large. But so is nickel, because it's actually over here with lesser effective nuclear charge. So when you have to compare these 2 things like this, I always say the group trumps the period rule. So that means that if you have something lower on a group, it's larger. So iodine is definitely going to be the larger of these 2. So iodine's larger, nickel's smaller, and when you're comparing the ionization energies of these 2, you have to consider that as well as their placement. Iodine wants to gain 1 electron, because when it gains 1 electron, it gets to be like the cool kids, in this case, xenon. So it does not really want to be ionized. It's going to have a very high level of ionization energy needed. Nickel is not really, it's kind of in that gray area, so it doesn't really have the desire to gain or lose electrons because it's not really close to either end of the spectrum here. So with that gray area being kind of the giveaway here, the gray area means that this, even though this one's larger, this iodine still has the highest ionization energy, therefore nickel would have the lower ionization energy. Let's do one more. Let's do chromium and tungsten. Chromium is up higher, tungsten is down lower. Tungsten wins because it's closer to the ionization energy here, the lower corner. Which of the following has the greater electronegativity? So this one means you desire electrons in a bond, in a covalent bond. This increases the same way ionization energy does. So there's my little cheat sheet arrow there. Between calcium and gallium, this is a period trend. The ZEFF increases this way towards the gallium. That means that it has a higher hold on its electrons. Who prefers to share still, though, or who prefers to steal the electrons more in a bond? That would definitely be gallium. So the greatest one's going to be closest to this corner up here. Lithium and oxygen. There's lithium, there's oxygen. Oxygen is definitely closer to this little, the farthest away from the corner, so it's the most electronegative. This one is actually very electronegative, and it prefers to steal electrons as much as possible in a bond. One more here. Let's do bromine and arsenic. Here's bromine, here's arsenic. Same situation. Bromine totally wants one more electron. One more electron gets it to be like krypton, which is a noble gas. Arsenic would have to gain 2 more. So bromine would be a great thief of electrons in a shared bond. One more here. I'll let you guys do this one. We just did an atomic radius one because this has been on the MSL for 2 years now. So I want to make sure that you're really familiar with these. So I'd like for you to try this one yourself. Let me know if you have questions. All right, we will be reviewing soon. All right, you have everything you need. You can try problem set 6. Reading guide 6 we will do in class next week, but I need you to try to remember to do little bit of this as you can, especially if you're stuck in the snow. See you soon.